Have you ever stopped to think about what's really going on inside the objects all around us? I mean, from the bridge you drive over to the phone in your hand, every single thing is in a constant, invisible battle against forces. And understanding this secret world of push and pull, well, that's the key to engineering pretty much everything. I mean, seriously, think about it for a second. Right now, you're putting a force on your chair, so why doesn't it just give up? Why doesn't it just splinter into 100 pieces? It seems like such a simple question, but trust me, the answer is absolutely fascinating. Well, the reason that chair is holding you up is because on a microscopic level, it's fighting back. It's resisting. It's pushing and pulling within itself to perfectly counteract the force of you sitting down. And that hidden world, that's exactly what we're diving into today. All right, so here's our game plan. First, we're going to learn the basic language of materials. Then we'll watch one fail in glorious slow motion. We'll get into their unique personalities, see what happens when things get twisted, and finally, see how engineers use all this to build a world that, doesn't fall apart. Okay, first things first. To understand this secret world, we gotta learn the lingo. And it all starts with two really fundamental words that describe how any material talks back to a force. The first word is stress. The best way to think about stress is that it's the material basically gritting its teeth. When you apply an outside force, what we call a load, the material creates an equal and opposite force on the inside to fight back. Stress is just the measurement of how intense that internal fight is. And the second word, that's strain. So if stress is the internal fight, strain is the visible consequence. It's how much the material actually changes shape, how much it stretches or gets squished compared to how big it was to begin with. It's the physical proof that a battle is going on inside. So let's nail this down, because it's super important. Stress is the cause. It's that invisible resistance happening on the inside. Strain is the effect, the physical change in shape we can actually see and measure on the outside. You just can't have one without the other. Okay, now for the fun part. Let's put these ideas into action. We're going to follow the entire life story of a steel bar as we pull it apart, from its first tiny stretch to its final dramatic snap. This graph right here, the stress-strain curve, it's like a biography of that steel bar. At first, it's in the elastic region. It stretches, but it can snap right back, no problem. But then, it hits the yield point. That's the point of no return. It's now permanently stretched. And get this is so cool. After that, it actually gets stronger for a bit. That's called strain hardening, and it's a crucial warning sign that things are getting serious. Finally, it hits its absolute maximum strength, the ultimate stress, and then it starts to neck down, focusing all that force on one tiny spot until, pop, it fractures. Now, that whole dramatic story we just saw, that was steel's personality. Every single material has its own unique story, its own curve, and understanding these different personalities is exactly how engineers know to use rubber for a tire and steel for a skyscraper. Let's talk about two of the biggest personality traits, elasticity and plasticity. Elasticity is super simple. It's the bounce-back ability. Think of a rubber band. You stretch it, you let go, it goes right back to its original shape. Plasticity is the opposite. It's the I'm bent and I'm staying that way trait. Think of a paperclip. Once you bend it, it doesn't spring back. It's been plastically deformed. Now, for two traits that people mix up all the time, toughness and hardness. Toughness is basically a material's ability to take a punch, how much energy it can absorb before it finally breaks. Hardness, on the other hand, is its ability to resist a scratch or a dent. A ceramic plate, for instance, is very hard but not very tough. You drop it, it shatters. A car bumper is the opposite. It's super tough, but you could scratch it with your keys. So far, we've mostly talked about just pulling something apart in a straight line. But the real world is way more complicated than that. Materials get bent, slid past each other, and twisted in all sorts of crazy ways. So let's see how that works. It really boils down to three big ones. You've got bending, which is a total diving board situation. The top gets stretched, the bottom gets squished. Then there's shear. Just think of scissors cutting paper. The two blades are sliding right past each other. And finally, there's torsion, which is just a fancy word for twisting force, like wringing out a wet towel. So how do engineers handle all this complexity? Well, they've got some powerful tools. Take this, the Flexure formula. It might look like a random jumble of letters, but it's basically a crystal ball for beams. It lets an engineer predict exactly how much stress a beam will feel from bending before a single piece of it is ever made.
Now this is really interesting. What this table shows us is that when it comes to shear forces, shape is everything. Look at this. For the exact same force, a circular beam handles the peak stress better than a rectangular one. It just goes to show you how a simple design choice can make something dramatically stronger. And it's the same deal for anything that twists. For a drive shaft in a car or an axle on a machine, the torsion formula is the absolute hero. It's what allows engineers to make sure these parts can transfer all that power without just twisting themselves into a pretzel. Okay, so we've learned the secret language, we've seen materials live their dramatic lives, and we've twisted and bent them. So what's the big takeaway? How do engineers use all this knowledge to actually build a safe, reliable world?
It all comes down to one golden rule: keep it elastic. Remember that point of no return from the steel bars story? The single most important goal in pretty much all of structural design is to make sure the real-world stresses a part experiences never, ever push it past that point. As long as it stays elastic, it can do its job and bounce back day after day for years. And in the end, that's what this entire field of science is all about. It gives us the tools to stop guessing and start knowing. We can predict how things will behave, we can calculate the forces, and we can design a world where things just work. So, I'll leave you with this final thought. We've pretty much mastered the personalities of steel, concrete, and plastic. But as we look to the future, to building things on Mars, to creating smarter cities here on Earth, what new materials are out there waiting to be discovered? What kind of incredible toughness, or weird elasticity, or even self-healing powers will they have? What will their stories look like? Well, that's the next chapter.